The room you are sitting in right now feels anchored to a single relentless truth. If you look at the walls, the furniture, or the palms of your hands, everything seems to be participating in the exact same moment. You feel yourself moving through this moment like a passenger on a train, looking out the window as the landscape of the past recedes and the terrain of the future rushes in to meet you. This passage feels absolute, uniform, and entirely independent of your opinion on the matter. It is the canvas upon which your entire life is painted. Every memory you possess is stamped with a date. Every plan you make relies on the promise that tomorrow will arrive precisely on schedule. We treat this flow as the fundamental bedrock of existence. Yet, when the tools of modern inquiry are turned directly upon this bedrock, it does not merely crack, it dissolves entirely. What we discover is a hidden room beneath the familiar architecture of reality, a place where the rules of common sense no longer apply. To understand how deep this rabbit hole goes, we have to look past our immediate impressions and ask a deceptively simple question that has haunted human thought for millennia. What precisely is time? If you try to answer this without using words like before, after, change, or duration, you will quickly find yourself trapped in a linguistic maze. Every definition we attempt to construct inadvertently smuggles in the very concept we are trying to isolate. This frustration is not new. In ancient Athens, Aristotle wrestled with this exact paradox in his foundational treatise, the Physics. He observed that time is deeply intertwined with alteration, ultimately proposing that time is the measure of motion. For over 2,000 years, this elegant formulation sufficed for the practical business of human civilization. If the stars moved across the night sky, or if sand slid through the narrow neck of an hourglass, we could count those intervals. The count was time. It was an objective, universal background rhythm that everyone shared. This comfortable certainty survived until 1905, when an obscure clerk named Albert Einstein upended the foundation of classical physics from a patent office in Bern, Switzerland. With the publication of his paper on special relativity, Einstein shattered the idea that motion and time exist independently of one another. He demonstrated that the rate at which time passes is intimately bound to how fast an object is moving through space. The faster you travel, the slower your clock ticks relative to someone standing still. This revelation turned Aristotle's ancient definition into a circular trap. If time is the measure of motion, but motion itself alters the passage of time, then the two concepts are leaning against each other like a pair of playing cards, neither capable of standing on its own. Long before this relativistic revolution, Sir Isaac Newton had attempted to bypass this confusion altogether. In his 1687 masterpiece, The Principia, Newton laid down the mathematical laws that still govern how we build bridges and launch satellites. When it came to the nature of duration, he simply asserted that absolute, true, and mathematical time of itself and from its own nature flows equably without relation to anything external. It was less an explanation and more of a cosmic axiom, a declaration that time was a grand universal metronome ticking away in the background of the cosmos, entirely indifferent to the material world. Not everyone was convinced by Newton's declaration. The philosopher Gottfried Wilhelm Leibniz engaged in a fierce, protracted correspondence with Newton's representative, Samuel Clarke, arguing that time could not possibly exist as an empty stage. Leibniz asked a biting question. If time is an independent entity that flows on its own, what does it flow relative to? A river flows past its banks. A pendulum swings relative to the floor. What is the cosmic clock ticking against? Newton had no answer, and physics eventually chose to ignore the philosophical dilemma, treating time as a convenient background parameter because the mathematics worked flawlessly. By the mid-20th century, the mystery had only deepened. When the legendary theoretical physicist John Archibald Wheeler, the man who coined the term black hole and worked alongside Richard Feynman, was asked to define the phenomenon, he offered a famous, witty evasion. Time is what keeps everything from happening all at once. It was a brilliant observation of time's utility, but a complete confession of ignorance regarding its substance. It echoed the profound frustration expressed 16 centuries earlier by the theologian Augustine of Hippo in his Confessions, where he lamented that he knew exactly what time was until someone asked him to explain it. Across a vast gulf of human history, the sharpest minds in science and philosophy arrived at the exact same wall. Perhaps the mistake lies in trying to capture time with language at all. We cannot define the experience of the color blue to someone who has never possessed sight. We can only measure its wavelength. And when it comes to measurement, humanity has achieved a level of terrifying precision. In 1967, scientists abandoned astronomical cycles and redefined the second based on the fundamental properties of the universe. They chose the cesium-133 atom, decreeing that 1 second is exactly 9,192,631,770 oscillations of the radiation produced by this atom transitioning between two specific energy states. By the 21st century, this technology evolved into optical lattice clocks using strontium atoms. These instruments are so astonishingly stable that they could run for the entire 13.8 billion year age of the universe and lose less than a single second. Yet these hyper-precise devices reveal an unsettling truth when we examine what they are actually doing. They are not measuring a mystical fluid called time. They are counting the internal vibrations of matter. We have merely agreed to label a specific tally of those vibrations as a second. Furthermore, these modern clocks are so sensitive that they reveal time to be a fluid, localized phenomenon. If you lift an optical strontium clock by a mere single centimeter, the slight reduction in Earth's gravitational pull causes it to tick measurably faster. The clock higher up experiences a different reality than the clock on the floor. We have built tools capable of slicing reality into billionths of a billionth of a second. Yet the thing we are measuring remains entirely elusive, an artificial construct layered over the inherent rhythms of atomic physics. This brings us to another characteristic of time that feels entirely non-negotiable: its direction. The past feels set in stone, populated by memories of things that can never be undone. The future feels open, a realm of possibilities yet to be realized. We witness this unidirectional flow everywhere. An egg dropped on a kitchen floor shatters, its yolk spreading across the linoleum. It never spontaneously gathers itself back together and leaps upward into its shell. A hot cup of coffee left on a desk cools down to match the temperature of the room. It never extracts ambient heat from the air to bring itself back to a boil. We call this the arrow of time. Strangely, if you look at the fundamental equations that describe how the universe works at its deepest levels, this arrow completely vanishes. In the 1950s, the physicists Gerhard Luders and Wolfgang Pauli established the CPT theorem, a mathematical proof demonstrating that the laws of nature remain perfectly symmetrical if you simultaneously invert charge, parity, and time. If you take the fundamental equations of physics and replace the time variable with its negative counterpart, the math works just as beautifully. James Clerk Maxwell's 19th century equations for electromagnetism do not care if time runs forward or backward. The Schrödinger equation, which dictates the behavior of the quantum world, is perfectly time reversible. Even Einstein's field equations for general relativity exhibit this symmetry. A video of a planet orbiting a star looks mathematically identical whether it is played forward or in reverse. The cosmos, at its most elemental level, makes no distinction between the past and the future. If the underlying laws of reality are indifferent to direction, why is ordinary life so fiercely dictated by the forward march of time? The breakthrough came in 1872 from a brilliant and tragic Austrian physicist named Ludwig Boltzmann. He realized that the arrow of time is not a fundamental law inscribed into the fabric of space, but rather a statistical illusion born from the concept of entropy. Entropy is often described as a measure of disorder, but it is more accurately understood as a game of cosmic probability. Consider a pristine jigsaw puzzle fresh out of the box. There is only one specific arrangement of the pieces that forms the complete picture. This is a state of extremely low entropy. If you put those pieces into a box and shake it, you will inevitably end up with a jumbled mess. There are millions of chaotic ways for those pieces to sit inside the box, but only one way for them to form the perfect picture. The universe does not possess a malevolent desire for chaos. There are simply vastly more ways for a system to be messy than there are for it to be neat. Boltzmann formalized this with his H theorem, demonstrating that any complex system will naturally drift toward the most statistically probable configuration. This drift is what we perceive as the flow of time. The coffee cools because there are infinitely more ways for its heat energy to disperse into the surrounding air molecules than there are for that energy to remain concentrated in the mug. The shattered egg stays broken because the number of broken arrangements astronomically outnumbers the single, highly specific arrangement of a whole egg. However, Boltzmann's brilliant solution contained a profound, unsettling catch. For entropy to be steadily increasing today, the universe must have started in an unimaginably ordered, low entropy state at the moment of the Big Bang. This requirement is known in modern philosophy of physics as the past hypothesis, a term coined by David Albert in 2000. It is an arbitrary boundary condition that cannot be derived from any deeper physical principle. We must simply accept that the universe began in a state of exquisite, highly improbable neatness. How improbable was this beginning? The mathematical physicist Roger Penrose calculated the odds of our universe emerging with an entropy low enough to create the arrow of time we observe. The number he arrived at is 1 part in 10, raised to the power of 10, raised to the power of 123. This is a number so monstrously large that you cannot write it out in standard notation. There are more zeros in the exponent than there are atoms in the entire observable universe. Every breath you take, every memory you form, and every clock that ticks relies on the universe having won this inconceivably rare cosmic lottery at the dawn of existence. To escape the sheer improbability of the past hypothesis, some physicists have suggested that our perspective on the arrow of time might be entirely backward. In 2004, Sean Carroll and Jennifer Chen proposed a model where the universe did not begin in a highly special low entropy state. Instead, they hypothesized that the primordial state of existence was one of total equilibrium, a vast, featureless, maximum entropy void where nothing happened and no time existed. In this model, random quantum fluctuations can occasionally pinch off small pockets of space, creating new baby universes. Crucially, these fluctuations can trigger an increase in entropy in opposite directions simultaneously. Imagine a perfectly flat table with a small pool of water resting in the center. If the table suddenly buckles upward in the middle, the water will flow outward toward both edges at the same time. According to Carroll and Chen, our universe is merely one of these branches. Our sense of forward is defined entirely by the direction in which entropy is growing along our specific path. On the other side of the fluctuation, an observer would experience time flowing in the exact opposite direction. To them, their arrow would feel just as natural, objective, and absolute as ours does to us. If this hypothesis holds, the arrow of time is not a global truth woven into the cosmos, but a purely local geographical feature, a consequence of which side of the cosmic hill we happen to be sliding down. If the direction of time can be reduced to a local perspective, what does that mean for the sanctity of the present moment? We live our lives with the absolute conviction that the now is a universal reality. We imagine that right now, across the vast expanses of the cosmos, from the next room to the most distant galaxy, the same instantaneous moment is occurring. Yet, Einstein's special relativity permanently dismantled this illusion by demonstrating the relativity of simultaneity. Einstein proved that two events that appear to happen at the exact same time for an observer standing still will happen at completely different times for an observer in motion. This is not an optical illusion caused by the time it takes light to travel to our eyes. It is a structural fact of the universe. Imagine you are standing precisely halfway between two withered trees. Suddenly, two bolts of lightning strike both trees at what appears to you as the exact same instant. Because you are equal distance from both flashes, the light waves reach your eyes simultaneously, and you declare the events to be concurrent. Now, imagine a passenger traveling past you on an ultra-high-speed train at the precise moment the lightning strikes. Because the train is moving toward the tree on the right and away from the tree on the left, the light from the right-hand bolt will reach the passenger slightly before the light from the left-hand bolt. To the observer on the train, the right tree was struck first and the left tree was struck second. The profound realization of relativity is that neither observer is wrong. There is no cosmic referee, no universal clock floating in the ether that can dictate who holds the true version of events. Both perspectives are perfectly valid descriptions of reality. The concept of a universal now is a fiction. Every object in the universe carries its own personal time frame, determined entirely by its speed and its position within a gravitational field. In 1908, the mathematician Hermann Minkowski, who had once taught a young Einstein, realized the radical implication of this fluidity. If space and time can stretch and contract depending on motion, they cannot be separate entities. Minkowski proposed that they are fused into a rigid, four-dimensional structure known as spacetime. He famously declared that henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. This conceptual framework is known as the block universe. In this view, the past, the present, and the future all exist simultaneously within a monolithic, unchanging four-dimensional block. Think of a featureless highway stretching across a continent. The city you left behind 3 days ago has not ceased to exist just because it is no longer outside your window. It remains fixed at its specific coordinates. The city you will reach tomorrow is already there, waiting for you to arrive. In the block universe, your birth, your current reading of these words, and your ultimate demise are all permanently etched into the fabric of space-time. They are all equally real. The sensation that you are moving through time, that the past is dead and the future is an unwritten void, is an illusion. It is a limitation of human consciousness, which can only perceive this grand, static architecture one thin slice at a time. While the block universe sounds like an esoteric philosophical concept, it was proven to be an undeniable reality of our world in 1971 through the Haffel-Keating experiment. The physicists Joseph Haffel and Richard Keating took 4 commercial atomic cesium clocks and flew them twice around the world on commercial airliners, once eastward and once westward. When the airborne clocks were compared to the reference clock that had remained stationary at the United States Naval Observatory, the data revealed an undeniable divergence. The clocks that flew eastward, moving in the direction of the Earth's rotation, had lost 59 nanoseconds. The clocks that flew westward, moving against the planet's rotation, had gained 273 nanoseconds. The passage of time had physically altered for these instruments simply because they had traveled at different speeds and experienced different gravitational pressures than the clock left on the ground. This relativistic drift is not an anomaly confined to physics laboratories. It is actively managed by a technology that billions of people use every single day. The global positioning system relies on a constellation of roughly 24 satellites orbiting the Earth at high speeds. Because these satellites are moving quickly relative to the ground, special relativity dictates that their onboard clocks should lose about 7 microseconds per day. At the same time, because they sit much higher up in the Earth's gravitational well, general relativity dictates that they should run faster by about 45 microseconds per day. When you combine these two competing effects, the clocks in orbit run fast by exactly 38 microseconds every single day. If the engineers who designed the GPS network had ignored Einstein's equations, the system would rapidly lose its accuracy. Within just 24 hours, the location data calculated by your smartphone would be off by more than 10 kilometers, rendering navigation apps completely useless. Every time you use your phone to find a local coffee shop, you are holding a device that actively corrects for the fact that time is an elastic, fractured phenomenon that moves at different speeds depending on where you stand. If the external world of physics reveals time to be a localized, illusory construct, we might still take comfort in our internal experience. Surely, the voice speaking inside your mind right now is experiencing a genuine, continuous, unedited flow of moments. Yet if we turn our attention inward, cognitive neuroscience reveals that this internal sense of a smooth, unbroken present is an elaborate illusion manufactured by the brain. In 1983, the neuroscientist Benjamin Libet conducted a groundbreaking experiment that sent shockwaves through the scientific community. He placed participants in front of a specialized clock and attached electrodes to their scalps to measure electrical activity in the motor cortex. He instructed them to flex their wrist whenever they felt an internal urge to do so, and to note the exact position of the clock hand when they made the conscious decision. Libet monitored three distinct milestones: the onset of the brain's electrical preparation for movement, the participants' conscious awareness of their intention to move, and the actual physical contraction of the wrist muscles. Common sense dictates that the conscious decision must come first, triggering the brain to send a signal to the muscles. The actual data revealed a startling reversal. The brain's motor cortex began generating an electrical signal known as the readiness potential, roughly 350 milliseconds before the participant became consciously aware of their own decision to move. The physical machinery of the brain had already committed to the action before the conscious mind experienced the illusion of making a choice. The felt sequence of intention leading to action is a narrative constructed after the fact, a retrospective rewrite designed to maintain the illusion of conscious control over time. Beyond the mechanics of decision making, our ordinary perception of the present moment is itself a heavily edited production. Our brains are constantly bombarded by a chaotic influx of sensory data, and these signals travel through our nervous system at radically different velocities. Sound waves travel through the air slower than light, but the auditory nerves process signals faster than the visual system. Furthermore, a tactile sensation from your big toe takes significantly longer to reach your brain than a sensation from your nose, simply because it has a longer distance to travel along the neural pathways. If your brain presented this data to you in real time, your reality would be a disjointed, chaotic mess. You would hear a person's words before seeing their lips move. You would feel a stubbed toe long after seeing the impact. To prevent this confusion, the brain acts as a cosmic editor. It implements a temporal buffer, holding on to the faster signals while waiting for the slower ones to arrive, stitching them together into a single, synchronized package. What you experience as the absolute now is actually a delayed broadcast, a curated production that occurred anywhere from 80 to 500 milliseconds in the past. We can catch the brain in the middle of this editing process through a perceptual anomaly known as chronostasis, or the stop clock illusion. If you rapidly shift your gaze from a random object to a ticking analog clock, the first movement of the second hand can appear to freeze, lingering in place for noticeably longer than a single second. This happens because during a rapid eye movement, your visual system becomes blurred and unusable. Rather than presenting you with a disorienting flash of motion blur, the brain suppresses visual awareness during the movement. Once your eyes settle on the clock face, the brain takes the first clear image it receives and projects it backward in time to fill the gap created by the movement. It creates a seamless story, covering up its own temporary blindness by stretching the present moment into the past. The brain also manipulates time to enforce our understanding of cause and effect. In 2002, the neuroscientist Patrick Haggard demonstrated a phenomenon called temporal binding. In his experiments, participants pressed a button that triggered a brief electronic tone after a fixed delay of 250 milliseconds. When asked to estimate the exact timing of their action and the resulting sound, participants consistently reported pressing the button later than they actually had and hearing the tone earlier than it had actually played. The brain had actively warped their perception of duration, pulling the cause and the effect closer together in time. It compresses the interval to ensure that the relationship between action and consequence feels immediate and intuitive. This entire psychological construct is tied to a specific biological metronome. Inside your skull, populations of neurons fire in synchronized rhythmic waves. One specific frequency, the gamma rhythm, oscillates between 30 and 100 times per second. Neuroscientists believe this rhythm serves as the processing speed for conscious awareness, the cadence at which the brain samples sensory information and binds it into distinct frames of experience. If this internal clock were immutable, we might argue that human consciousness possesses a stable, objective time frame. However, this biological rhythm is remarkably fragile. In 2016, a study led by Anrio Tagliazucchi demonstrated that introducing substances that alter brain chemistry can disrupt the synchronization of these gamma waves. When the neural rhythm fragments, the different regions of the brain begin processing information out of sync. As a result, the subject's experience of time collapses. Seconds can warp into agonizing hours, or hours can vanish in the blink of an eye. Similar distortions occur naturally under conditions of extreme duress. When a person is involved in a car accident or falls from a significant height, they often report that the event appeared to unfold in extreme slow motion. This stretching of time is a consequence of the amygdala shifting into a hyper-alert state, increasing the brain's sensory sampling rate. Because the brain records a vastly denser volume of information during those terrifying seconds, the memory retrieval process interprets the event as having lasted far longer than it actually did. The internal clock is an elastic piece of biological software easily bent by fear, chemistry, or deep meditation. If time dissolves into an illusion when examined through the lens of macrophysics and reveals itself to be a biological fabrication when viewed through neuroscience, we are forced to look even deeper. If time is real anywhere, it must exist at the foundational level of reality, the quantum realm. Yet, it is precisely here that the concept of time suffers its most radical defeat. In 1978, John Archibald Wheeler proposed a thought experiment known as the delayed choice experiment. He imagined a single photon fired toward a beam splitter, a half-silvered mirror that offers the particle two possible paths to travel, path A or path B. According to the bizarre rules of quantum mechanics, if you place a detector along each path, the photon behaves like a solid particle, choosing one route and triggering only one detector. However, if you leave the detectors out and instead use mirrors to bring the two paths back together at a second beam splitter, the photon behaves like a wave. It travels both paths simultaneously, creating a distinct wave interference pattern on a final screen. Wheeler's radical twist was to ask, what happens if we decide whether or not to insert that second beam splitter at the very last microsecond, long after the photon has already passed through the first mirror and completed its journey through the apparatus? If the photon chose a single path as a particle or split into both paths as a wave at the beginning, uh, a choice made at the very end should not be able to alter that history. For decades, this remained a philosophical paradox, but in 2007, a team led by Vincent Jacques in Paris built a physical version of Wheeler's experiment using advanced quantum optics and a high-speed random number generator. The generator decided whether to insert or remove the second beam splitter while the photon was already mid-flight. The results were unequivocal. If the system decided to insert the second splitter at the last moment, the photon produced an interference pattern, proving it had traveled both paths as a wave. If the system decided to leave it out, the photon behaved like a particle, having traveled only one path. A conscious choice made in the present had actively dictated the physical behavior of a particle in the past. The experiment demonstrated that at the quantum level, the past is not a settled record. It remains fluid, waiting for a measurement in the now to retroactively cement what actually happened. This fluid relationship with history points toward a deeper mystery that strikes at the very heart of space and time: quantum entanglement. In 1964, the physicist John Bell proved a mathematical theorem demonstrating that two particles can become entangled, linking their physical states regardless of the distance separating them. If you measure the spin of one entangled particle on Earth, its partner on the far side of the galaxy will instantaneously alter its spin to match, defying the universal speed limit of light. Einstein famously dismissed this as spooky action at a distance, believing it violated the core tenets of relativity. Yet, decades of rigorous testing have proven Bell's theorem to be correct. The correlation is instantaneous. This creates an irreconcilable conflict with our understanding of time. If the adjustment is instantaneous, it requires a universal now, a single moment shared across the universe to coordinate the behavior of both particles. Yet, as special relativity proved, a universal now cannot exist. The order of events depends entirely on your frame of reference. For an observer moving in one direction, particle A changed before particle B. For an observer moving the other way, particle B changed before particle A. The quantum world refuses to comply with our linear narrative. It suggests that at the most fundamental layer of reality, space and time are not the primary building blocks of the universe. They are emergent phenomena, secondary illusions, arising from a deeper interconnected quantum reality that does not use a clock. We find ourselves stranded between two worlds. If we look out at the cosmos through the equations of relativity, time stretches, warps, and freezes, ultimately solidifying into a giant static block where every moment exists forever. If we look inward through the lens of neuroscience, the fluid passage of time is revealed to be a clever evolutionary trick, a story told by our neurons to help us navigate a chaotic environment. And if we look down into the quantum foundations of matter, the sequence of cause and effect breaks down entirely. The feeling you have right now, the quiet sensation of one moment sliding effortlessly into the next, smooth and unbroken like water, is a beautiful, necessary fiction. The hallway of your ordinary life remains perfectly functional, but the hidden room beneath it has been thrown wide open. The foundation of our reality is far stranger than we ever imagined, not because it is broken, but because the closer we look, the more we realize that time is not the rule by which the universe plays. It is simply the language we use to understand our place within it. To step completely through that open door is to confront a landscape where our most basic assumptions about existence begin to fray. We are accustomed to thinking of the universe as a vast container filled with three dimensions of space, inside of which the gears of time turn at a steady, unyielding pace. In this intuitive picture, matter and energy are the actors, space is the stage, and time is the ticking clock on the wall governing the entire production. But when we look at the contemporary frontier, where quantum mechanics attempts to merge with general relativity, the sought after realm of quantum gravity, this entire picture is turned on its head. The stage and the clock do not merely warp, they disappear from the fundamental equations altogether. This vanishing act is most famously illustrated by an equation formulated in the late 1960s by the physicists John Wheeler and Bryce DeWitt. In their attempt to create a wave function for the entire cosmos, a mathematical description that would apply quantum mechanics to the universe as a whole, they ran into a startling mathematical reality. When they finished constructing the equation, the variable representing time, the letter t, which populates almost every other equation in physics, had completely dropped out. The Wheeler-DeWitt equation describes a universe that is fundamentally static. It is an equation for a cosmos that simply is, a timeless network of relationships where change is not a primary ingredient, but a secondary, superficial appearance. For decades, this mathematical quirk was treated as a troubling paradox, a glitch in the machinery of theoretical physics that needed to be ironed out. After all, how could an equation that successfully describes our universe omit the very thing we experience most vividly? But a growing contingent of modern physicists suggests that the Wheeler-DeWitt equation wasn't a mistake at all. It was a direct transmission from the deepest layer of nature, telling us that time is not a fundamental building block of the cosmos. Instead, it may be what physicists call an emergent property. To understand emergence, you don't need a degree in theoretical physics. You only need to look at a glass of water. If you were to isolate a single H2O molecule, you could measure its mass, its velocity, and its electrical charge. But if someone were to ask you whether that single molecule is wet or fluid, the question would be meaningless. Wetness is not a property of a single molecule. It only appears when you gather billions of those molecules together and allow them to interact. Fluidity emerges from the collective behavior of things that are not themselves fluid. A radical school of thought in modern physics proposes that time functions in exactly the same way. At the most fundamental, microscopic scale of reality, well below the level of atoms, down at the Planck length where the fabric of spacetime itself becomes granular, there is no such thing as duration. There are no seconds, no past, and no future. There are only timeless quantum building blocks entangled with one another in a vast, intricate web. Time, on this view, is the wetness of the universe. It is a macroscopic illusion that only manifests when we zoom out and observe the collective behavior of countless microscopic states. If this sounds like an untestable philosophical speculation, An extraordinary experiment conceived in the 1980s by the physicists Don Page and William Wooters proved that you can actually create time out of timelessness using the magic of quantum entanglement. Imagine an isolated, closed quantum system that from the outside appears completely static. The total energy of the system is fixed, and its overall state never changes. According to the equations of quantum mechanics, time within this global system is completely dead. It does not tick. However, Page and Wooters demonstrated that if you divide this static system into two separate parts, say an observer's clock and the rest of the environment, and entangle them, something miraculous happens. If an observer inside the system looks at the clock, they will see its state shifting in perfect correlation with the changes in the environment. To the observer trapped within the entanglement, time appears to flow beautifully and continuously. Yet to an outside observer looking at the system as a whole, nothing is moving. Time is revealed to be a perspective born entirely from being entangled with the world you are trying to observe. The passage of time is not an intrinsic feature of the universe, but the relational currency paid by an observer who is inside the system looking out. This relational nature of time sheds a fascinating light on why our ordinary everyday world feels so fundamentally different from the timeless quantum underworld. It brings us to a process known as quantum decoherence. In the subatomic realm, particles exist in a state of superposition. They can be in multiple places at once, spinning in opposite directions simultaneously, suspended in a haze of pure mathematical probability where the past and future remain unwritten. But the moment a quantum particle interacts with its environment, colliding with a photon, a stray molecule, or the tip of a laboratory probe, that haze collapses. The particle is forced to choose a single, definite state. Decoherence is the bridge between the quantum and the classical world. It is a relentless, ongoing process happening trillions of times every second all around you. Every macroscopic object you see, from the chair you are sitting on to the moon orbiting the Earth, is constantly bombarded by countless environmental interactions. This endless crosstalk effectively washes away the delicate quantum superpositions, smoothing out the weirdness of the subatomic world into the predictable, solid reality we inhabit. Crucially, it is this very process of decoherence that records information about the past into the structure of the environment. When a photon bounces off a surface, it carries away information about where that surface was. This accumulation of information creates an asymmetric trail, a permanent record of what has occurred that cannot be undone. Time's arrow, which is completely absent from the individual, reversible equations of quantum mechanics, begins to crystallize the moment macroscopic systems interact. We experience a forward flow of time not because the universe is marching along a cosmic timeline, but because our macroscopic brains are riding the massive, irreversible wave of quantum decoherence, constantly digesting the information left in its wake. This realization that space and time might be secondary constructs rather than fundamental truths has sparked a major revolution in modern physics, the idea of holography. In 1997, a theoretical physicist named Juan Maldacena shocked the scientific community by demonstrating a mathematical equivalence between two completely different types of universes. On one hand, he described a five-dimensional universe that included gravity and behaved according to the rules of general relativity. On the other hand, he described a four-dimensional boundary that surrounded this universe, which had no gravity at all and operated purely on the laws of standard quantum mechanics. Maldacena proved that everything happening inside the five-dimensional interior could be mapped perfectly onto the flat, four-dimensional boundary, much like a three-dimensional holographic image is generated by the two-dimensional film of a credit card. In this holographic framework, the extra dimension of space and the gravitational forces acting within it are not fundamental. They are an illusion generated by the complex quantum entanglements occurring on the boundary surface. In recent years, physicists have extended this holographic principle to time itself. If space can emerge like a hologram from quantum relationships, then the temporal dimension, the very flow of moments, might also be a projection code generated by the complex networking of information. We are left with the staggering possibility that the universe we observe is not a physical space enduring through time, uh, but a cosmic projection whose apparent depth and duration are woven entirely out of quantum information. This view fundamentally alters how we conceive of memory, history, and our own mortality. In the classical view of reality, the past is gone, a ghost that exists only in the imperfect filing cabinets of our minds and the physical scars left on the world. The future is an unformed void, waiting to be sculpted by the present. But if the block universe of relativity and the timeless equations of quantum gravity are correct, the boundary between what was, what is, and what will be is nothing more than a stubborn cognitive persistent. When Albert Einstein's lifelong friend Michel Besso passed away in 1955, just a few weeks before Einstein's own death, the great physicist wrote a letter to Besso's family that captured this profound realization. He wrote, "Now he has departed from this strange world a little ahead of me. That means nothing. For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion." It was not a superficial expression of comfort. It was a literal statement of his scientific worldview. In the landscape of space-time, Besso's life was not erased. It remained a permanent, radiant feature of the four-dimensional block, bounded by specific coordinates, but forever intact. If we bring our focus back from the grand cosmic scale and look once more inside our own skulls, the neuroscience of time reveals an even more intimate paradox. We have established that the brain acts as an editor, delaying and binding sensory inputs to create a unified experience of now. But the brain does not just construct the present, it is also completely responsible for our perception of the past through the architecture of memory. And just as the physical universe refuses to maintain a clean record of history independent of observation, our minds refuse to treat memory as a simple, passive recording device. For a long time, the prevailing psychological intuition was that human memory functions like a vast digital archive. We assume that an event occurs, the brain writes that data onto the hard drive of the hippocampus, and when we want to remember it, we simply pull up the file and view it exactly as it was recorded. But decades of cognitive research have demonstrated that memory is not a retrieval system. It is an act of active reconstruction. Every time you recall a childhood memory, a conversation from last week, or even what you ate for breakfast this morning, you are not viewing a static file. You are pulling scattered fragments of information, visual cues stored in the visual cortex, emotional echoes in the amygdala, linguistic fragments in the temporal lobes, and forcing the brain to stitch them back together in real time. Crucially, during this process of retrieval, the memory becomes highly malleable. It is vulnerable to alteration influenced by your current emotional state, the environment in which you are remembering it, and the information you have acquired since the event occurred. When the brain finishes reconstructing the memory, it doesn't leave it floating around. It writes it back into the neural architecture. You are effectively saving a new version over the old file. This means that the more you remember a specific event throughout your life, the less you are recalling the original occurrence and the more you are recalling the last time you remembered it. Our internal anchor to the past is not a solid chain linked to an objective truth. It is a game of telephone our brain plays with itself across the span of decades. This reconstructive nature of memory serves an evolutionary purpose that has nothing to do with maintaining a historically accurate ledger. In the early 2000s, researchers using functional MRI scans discovered a striking neurological overlap between two mental tasks that feel completely distinct: remembering the past and imagining the future. When a participant was asked to recall a specific personal history, certain networks in the brain, collectively known as the default mode network, lit up in a distinct pattern. When those same participants were asked to imagine a completely novel scenario that might happen to them in the future, the exact same neural network flared to life. The brain uses the exact same toolkit to look backward as it does to look forward. This led neuroscientists like Daniel Schachter to propose the constructive episodic simulation hypothesis. The brain did not evolve its complex memory systems to keep us accurately informed about history. It evolved them as a survival engine designed to predict the future. The past is treated as a scrapyard of raw materials. Sensory fragments, behavioral outcomes, cause and effect relationships, that the brain can rapidly disassemble and reassemble into simulations of what might happen tomorrow. We do not look back to see where we were, we look back to guess where we are going. This predictive nature of consciousness explains why our internal experience of time can feel so violently disconnected from the steady ticking of an atomic clock. Consider the phenomenon of flow, that deeply satisfying state of mind experienced by athletes, musicians, and artists when they are completely immersed in a challenging task. During a state of flow, the self disappears, self consciousness vanishes, and hours can pass in what feels like a matter of minutes. Neurologically, this occurs because the task at hand matches the brain's predictive capacity so perfectly that the default mode network, the system responsible for constructing the narrative self and tracking the passage of time, is temporarily quieted. Because the brain is not constantly comparing the current sensory input against its memories to predict the next moment, the internal mechanism that generates the feeling of duration goes offline. You become a purely real time processing engine, detached from the very narrative structure that gives time its weight. Contrast this with the experience of profound boredom, intense pain, or acute anxiety. When you're trapped in a dull meeting, experiencing a severe migraine, or waiting for the results of a medical test, every single minute can feel like an eternity. In these states, the brain's predictive machinery is frustrated. It is constantly checking the environment, asking, is it over yet? Is the pain gone? What happens next? This hyperfixation forces the brain to sample the environment at a much higher resolution, generating an enormous density of experiential frames per second. When the brain reviews this period, the sheer volume of data forces the internal clock to interpret the duration as vastly elongated. Time stretches because the mind is working overtime to escape the current slice of reality. This elasticity of psychological time becomes even more pronounced as we age. It is a nearly universal human experience that as the decades slide by, time seems to accelerate. Summers that felt like endless lifetimes during childhood vanish in the blink of an eye during middle age. While part of this can be attributed to the mathematical reality that a single year represents a much smaller fraction of a 50-year-old's life than a 5-year-old's, neuroscience offers a deeper structural explanation related to how we process novelty. When a child experiences the world, almost everything is new. The brain is working furiously to catalog the unfamiliar sights, sounds, and social dynamics of its environment, burning deep, rich neural pathways to store this wealth of information. But as we grow older, the world becomes increasingly familiar. We develop cognitive routines, mental shortcuts, and behavioral habits. When a 40-year-old drives to work along a route they have taken thousands of times, the brain doesn't bother recording the details. It goes on autopilot, treating the journey as a single compressed unit of experience. Because the adult brain encounters fewer novel stimuli, it writes fewer distinct memories into its history books. When you look back at a year filled with routine, your brain finds a sparse, empty landscape with very few landmarks to mark the passage of duration. The mind reviews this lack of data and concludes that the year must have passed quickly. We accelerate as we age because we stop learning how to see the world for the first time. The clock speeds up when we allow our lives to become predictable. When we combine these internal neurological insights with the external revelations of quantum mechanics and relativity, we are left standing on a very strange precipice. The universe outside our heads is a four-dimensional block of static spacetime, where the past, present, and future coexist in a timeless web of quantum relationships. The universe inside our heads is a highly sophisticated simulator, constantly delaying sensory inputs, editing history, and warping duration to keep us alive in an unpredictable world. This means that the version of time we live by every day, the frantic schedule dictated by the alarms on our phones, the clean dividing line between our regrets and our anxieties, is a double illusion. It is a biological interpretation of an emergent physical phenomenon. We are like creatures living in a theater, convinced that the moving images on the screen represent the fundamental truth of the world, entirely unaware of the static film strip running through the projector, let alone the complex system of light and electricity that makes the projection possible. But as we noted at the very beginning of this exploration, this realization should not ignite a sense of dread or existential vertigo. It is not an eviction from reality. It is an invitation to view our lives through a wider, more profound lens. The fact that time is not a fundamental, absolute tyrant means that we are not helpless, leaves being swept down an unstoppable river toward total erasure. If the block universe is right, your childhood is not a ghost town that has ceased to exist. It remains permanently anchored at its specific coordinates in the fabric of the cosmos. The moments of joy, the profound connections, and the quiet spaces of peace you have experienced throughout your life are not fleeting sparks extinguished by the arrival of the next second. They are immutable features of existence, woven into the architecture of reality forever. And if the neuroscience of perception is right, it means you possess a remarkable, unspoken agency over the clock inside your own mind. If you wish to slow down the relentless acceleration of the years, the prescription is not to run away from time, but to actively disrupt the routines that make the brain go blind. By seeking out novelty, learning new skills, placing yourself in unfamiliar environments, and training your mind to attend to the raw, unedited details of the immediate present, you can force your brain to sample reality at a higher resolution. You can stretch the canvas of your life, expanding the felt duration of your days, simply by refusing to live them on autopilot. We will likely never build a clock that can look past the cesium atom to capture the ultimate substance of time itself. We will continue to build ever more precise instruments, measuring the vibrations of strontium atoms to a billionth of a second, relying on technologies that quietly adjust for the fluidity of spacetime in the palms of our hands, all while our brains continue to stitch together a unified now from the chaotic delays of our nervous systems. But tonight, as you watch the seconds tick away on the clock, you can do so with the knowledge that the hallway you walk through every day has that second hidden room behind it. A room where the past is never truly lost, the future is already waiting, and the present moment is a masterpiece painted by the collaborative genius of physics and human consciousness. We are not just passengers on a train rushing blindly through the dark. We are the observers whose very presence allows the landscape to come alive, turning a timeless, silent cosmos into a world that flows, changes, and means something. To push deeper still into this hidden room is to confront the realization that if time is an emergent illusion, then the very concept of change, the engine that drives our ambitions, our evolution, and our grief, must be reevaluated from its foundation. In the ordinary world, we look at a seed growing into a tree, or a star collapsing into a supermassive black hole, and we see an unfolding narrative. We see a sequence of states where state A causes state B, and state B gives way to state C. But if the equations of quantum gravity are telling the truth, this narrative structure is an artifact of our perspective. The universe is not an unfolding story. It is a vast, interconnected equation whose answers are all present simultaneously. This conceptual shift forces us to re-examine one of the most stubborn dilemmas in human history, the paradox of free will and determinism. For centuries, philosophers have argued that if the universe is deterministic, if the current state of the cosmos completely dictates the next state through the laws of cause and effect, then our choices are nothing more than the inevitable tumbling of cosmic dominoes. If you choose to drink a glass of water right now, that choice was already written into the positions of the particles at the moment of the Big Bang. Relativity's block universe takes this dilemma and makes it structural. In a four-dimensional block of spacetime, the future is not a fluid realm of potential waiting to be decided. It is already physically there. Your tomorrow is just as real, fixed, and unyielding as your yesterday. From this perspective, the traditional debate over free will becomes entirely reframed. The question is no longer whether your conscious mind can break the laws of physics to change the future. The question is why you feel like you are choosing at all. The answer, once again, brings us back to the relational boundary between the observer and the observed. In a timeless universe, your choices are not events that alter the timeline. They are the geometric lines that connect different parts of the block together. Think of a character in a novel. From the perspective of the reader holding the book, the protagonist's journey is already completely printed on the pages. Their tragic mistakes, their sudden triumphs, and their ultimate fate are fixed in ink. The character cannot leap off page 50 and change what happens on page 300. Yet, as the character lives through the narrative on page 50, they face genuine decisions. They weigh options, experience doubt, and take actions that feel entirely open to them. Their experience of choice is completely real within the context of the story, even if the book as a whole is static. We are the characters in the cosmic book of space-time. Our feeling of making a conscious choice is not an illusion in the sense that it is a lie. It is a true description of what it feels like to be a localized knot of information processing its environment from the inside out. You cannot change the future, not because you are a helpless slave to destiny, but because the future is already a part of the grand tapestry to which you belong. Your choices are the very threads that weave that tapestry together. Without your internal deliberation, your sudden insights, and your eventual actions, the future coordinates of the block universe would not exist in the shape that they do. You are not a passive spectator watching a movie that was filmed without you. You are the living machinery through which the static block defines its own structure. This understanding sheds a radical light on the nature of causality itself. In classical physics, we are taught that the past causes the present, which in turn causes the future. The arrow of influence points strictly in one direction. But as John Wheeler's delayed choice experiment demonstrated at the subatomic scale, quantum mechanics allows the present to reach backward and sculpt the nature of the past. When a physicist chooses how to measure a photon today, that choice determines whether the photon traveled as a wave or a particle billions of years ago. When we scale this principle up to the macroscopic world through the lens of modern cosmology, it suggests that the history of our entire universe might not be a single solid line running forward from the Big Bang. Instead, the universe may exist in a quantum superposition of countless possible histories. In the early 2000s, Stephen Hawking and Thomas Hertog proposed a framework known as top-down cosmology. They argued that instead of trying to construct a theory that starts at the beginning of the universe and predicts what it looks like today, we must do the exact opposite. We must start with our current observations of the universe. The fact that it has three dimensions of space, an arrow of time, and conditions suitable for life, and use those observations to retroactively select the specific quantum histories that could have led to this moment. In top-down cosmology, the past does not exist in a definite state until it is measured in the present. The early universe did not possess a single, concrete reality that slowly unreeled into the modern world. It was a haze of probabilities, a chaotic matrix of potential timelines. It was only when conscious observers emerged within the system, measuring the cosmos and asking questions about its origins, that the universe was forced to collapse its quantum wave function, retroactively freezing a single coherent history into place. We are not just the products of cosmic history. We are the authors whose current existence calls that history into being. This reciprocal relationship between the mind and the cosmos implies that our ordinary perception of time is not a passive recording of reality, but an active, creative interpretation optimized for survival. If human consciousness had evolved to perceive the universe as it truly is, a static, four-dimensional block of quantum information, we would have gone extinct before we ever left the primordial oceans. A creature that experiences all of its internal states simultaneously, unable to distinguish between a threat that is happening now and a threat that happened yesterday, cannot hunt, cannot flee, and cannot reproduce. The linear flow of time is an evolutionary filter. It is a biological user interface designed to compress an overwhelming multidimensional reality into a simple sequential narrative that our limited brains can manage. Think of the desktop interface on your computer. When you drag a file into the trash icon, you see a simple visual animation of a piece of paper sliding into a bin. But that animation is not what is actually happening inside the computer. In reality, the machine is executing millions of complex calculations, shifting electrical charges across transistors, and reallocating magnetic bits on a silicon chip. If you had to manually manipulate those electrical charges just to delete a document, you would never be able to use the computer. The desktop interface hides the true complexity of the machine behind simple, intuitive icons so that you can interact with it effectively. The present moment is the desktop interface of human consciousness. The complex quantum entanglements, the static four-dimensional geometry of spacetime, and the chaotic vibrations of atoms are all hidden behind the simple, intuitive icons of now, then, before, and after. We live in the simulation because the simulation is the only place where life can function. This realization transforms how we think about the biological machinery that maintains this interface. We have looked at how the brain edits the sensory present and reconstructs the historical past, but neuroscience has recently begun to uncover the specific physical brain regions that act as the master engineers of this temporal illusion. It turns out that the brain does not possess a single centralized clock. Instead, it relies on a decentralized network of internal timekeepers, each tuned to a different scale of existence. For the grand, sweeping cycles of life, the daily rhythm that tells you when to wake, when to eat, and when to sleep, the body relies on the suprachiasmatic nucleus, a tiny cluster of roughly 20,000 neurons nestled inside the hypothalamus. This master circadian clock is hardwired directly to your optic nerves, constantly sampling the ambient light of the environment to keep your biological rhythms synchronized with the rotation of the Earth. If you lock a human being inside a completely dark cave, stripped of all clocks, windows, and seasonal cues, the suprachiasmatic nucleus will continue to tick on its own, maintaining an internal cycle that drifts only slightly away from the standard 24-hour day. It is our ancient evolutionary anchor to the astronomical dance of the cosmos. But when it comes to the sub-second intervals, the tiny fractions of a duration required to catch a falling glass, speak a sentence, or appreciate the rhythm of a piece of music, the brain bypasses the circadian clock entirely. It turns instead to the basal ganglia and the cerebellum. The basal ganglia function as a sophisticated stopwatch, utilizing loops of electrical activity that pulse through the cortex to measure precise intervals of duration. When you anticipate the beat of a drum or tap your foot in time with a song, you are relying on these deep subcortical structures to slice reality into predictable fragments. Meanwhile, the cerebellum acts as the brain's ultimate computational engine for motion and spatial timing. It calculates the exact microsecond delays required for different muscle groups to coordinate their movements through space. When a professional athlete hits a baseball traveling at 100 miles per hour, their conscious mind has no time to deliberate. The visual information hasn't even finished being processed by the primary visual cortex before the cerebellum has already calculated the trajectory, adjusted the angle of the arms, and initiated the swing. The athlete is operating entirely within the blind spot of the biological present, guided by a biological computer that operates faster than conscious awareness can follow. What happens when these internal timekeepers begin to fail? The breakdown of the brain's temporal machinery offers some of the most haunting and insightful glimpses into the true fragility of our relationship with time. Consider the condition known as Korsakoff's syndrome, a neurological disorder typically caused by severe thiamine deficiency. Patients suffering from Korsakoff's lose the ability to form new long-term memories. Their short-term memory buffer lasts for only a few seconds before resetting entirely. A person with Korsakoff's is permanently stranded in a terrifyingly narrow window of existence. If you walk into the room, shake their hand, and introduce yourself, they will greet you with perfect clarity and intelligence. But if you turn around, step out the door for 5 seconds, and walk back in, they will have absolutely no recollection of ever having met you. For them, you are a completely new stranger, walking into their lives for the very first time. Because their brain cannot stitch the immediate past into a continuous narrative thread, their sense of duration collapses into a sequence of isolated, disconnected frames. They are trapped in an eternal, looping present, unable to build a bridge back to their history or project a pathway into their future. To witness a person in this state is to realize that without the constant automatic reconstruction of memory, the human soul becomes unanchored, floating like a ghost in a timeless void. On the opposite end of the spectrum sit those rare individuals who possess a condition known as highly superior autobiographical memory, or HSAM. A person with HSAM can recall almost every single day of their life with terrifying cinematic precision. If you give them a random date from 20 years ago, say the 3rd of October 2006, they can tell you instantly what day of the week it was, what the weather was like, what they wore, what they ate for lunch, and the exact details of the conversations they had. For an individual with HSAM, the past is never permitted to fade into a sparse, compressed landscape. Their brain refuses to delete the routine, mundane details of existence. While this might sound like a superpower, many people living with HSAM describe it as an exhausting burden. The weight of their history is constantly pressing against their present awareness. They cannot forgive and forget because the emotional scars of an argument that happened decades ago feel just as raw, vivid, and immediate as if it had occurred 5 minutes ago. Their internal block universe is crowded with an overwhelming density of data, proving that our ordinary ability to forget, to compress and erase the structural details of our days, is a vital survival mechanism designed to keep us from being crushed by the sheer volume of our lives. When we look closely at these neurological extremes, we see that our ordinary sanity depends on a delicate, perfectly balanced calibration of our internal temporal interface. The brain must hold on to the past just enough to give us a sense of identity and direction, but not so much that we are paralyzed by its weight. It must delay the present just enough to create a synchronized, stable image of the world, but not so much that we are unable to react to immediate dangers. We are walking a razor-thin biological tightrope, suspended over a boundless ocean of timeless quantum information. This realization forces us to confront a profound question about the nature of our own consciousness. If time is an emergent property of the physical universe, and if our internal experience of time is a biological fabrication optimized for survival, then what happens to consciousness when the biological machinery stops? What happens to the observer when the clock finally runs down? In the classical, materialistic view of the world, the answer is simple and bleak. Consciousness is an ephemeral byproduct of neural activity, a spark generated by the friction of electrical current passing through brain tissue. When the heart stops beating, oxygen stops flowing to the cortex, the neurons exhaust their chemical reserves, and the electrical activity falls silent. The spark is extinguished, and the observer simply ceases to exist. The story ends, the screen goes black, and the void reclaims the space. But if we look at this transition through the lens of modern physics, through the block universe of relativity and the holographic principles of quantum gravity, the conclusion changes dramatically. In a universe where space and time are fused into a static, four-dimensional block, your life is not a brief candle flame that burns for a few decades and then disappears into the dark. Your life is a solid, immutable structure permanently etched into the geometry of the cosmos. Imagine a beautiful crystal sculpture frozen inside a massive block of ice. The sculpture doesn't travel through the ice. It doesn't appear at one end and vanish at the other. It occupies a definite, permanent volume within the whole. Your birth is the beginning coordinate of that sculpture. Your death is the concluding coordinate, the period in between, the years you spent learning, loving, struggling, and reading these very words, is the intricate, beautiful shape of the sculpture itself. When you reach the end of your life, you do not fall off the edge of the world into a black abyss. You simply reach the structural boundary of your specific trajectory within space-time. From the perspective of an observer trapped inside the linear flow, your life appears to have ended, gone forever into the past. But from the perspective of the cosmos as a whole, your life remains exactly where it always was, completely intact, perfectly preserved, and eternally present. Every word you ever spoke, every tear you ever shed, and every moment of silent wonder you ever experienced remains a permanent, living feature of the universe. Death, on this view, is not the destruction of existence. It is simply the final frame of a masterpiece that can never be erased. This perspective offers a profound, grounded comfort that requires no appeal to mysticism or supernatural faith. It is a conclusion arrived at through the cold, rigorous mathematics of theoretical physics. It suggests that our current obsession with longevity, Our desperate, anxious race against the clock to squeeze as many years as possible out of our fragile biological vessels might be framed completely the wrong way around. The quality of a life is not measured by the length of its coordinate along the temporal axis of the block universe. It is measured by the depth, the beauty, and the complexity of the shape it traces within that space. A life that is short, but lived with intense awareness, deep connection, and profound creative expression forms a radiant, brilliant sculpture within the fabric of space-time. A life that is long, but lived in a dull, uninspired routine, on autopilot, numb to the wonder of existence, forms a flat, muted line. The clock will always run out, the biological vessel will always decay. But the shape you choose to carve into the universe through your actions, your choices, and your attention is yours to decide. This brings us back to the immediate present, to this very moment, right here, right now, as your eyes take in these final sentences. Look at the room around you once more. Listen to the faint ambient sounds filtering in from the outside world. Feel the steady rise and fall of your chest as you breathe. A few moments ago, before we began this journey into the hidden architecture of reality, this experience felt simple, ordinary, and entirely transparent. You took it for granted that you were a solid entity moving through an objective timeline, watching the world change around you. But now, you know the truth. You know that the timekeeping systems inside your phone are actively correcting for the fact that time moves at a different speed for the satellites in orbit than it does for the hands holding the device. You know that the fundamental equations of nature treat the past and the future with absolute, unyielding symmetry, completely indifferent to our human arrow of time. You know that your brain has intentionally delayed the visual data entering your eyes, holding it back to match the slower signals of your other senses, just to present you with a clean, edited illusion of a unified now. And you know that at the subatomic foundation of the room you are sitting in, space and time dissolve entirely into a timeless web of quantum information. You are standing in the center of a grand, collaborative miracle. The universe outside your head provides the vast, static canvas of space-time, an infinite block of potential histories and entangled relationships. The brain inside your skull provides the biological software, weaving that chaotic, timeless matrix into a smooth, continuous narrative that you can experience and understand. The flow of time is not a prison that holds us captive. It is a song sung by the mind in harmony with the cosmos. Tonight, as you lay your head down to sleep and allow the conscious interface to fade into the quiet dark of slumber, you can do so with a sense of peace. You do not need to fear the passage of the hours, or the steady ticking of the clock on the wall, or the slow, inevitable aging of your body. The river of time may be an illusion, but it is the most beautiful illusion ever created. It is the mechanism through which a static, silent cosmos discovered how to feel, how to change, how to remember, and how to love. And no matter how fast the years seem to accelerate or how uncertain the future may appear, nothing can ever alter the fact that you were here, participating in the dance, carving your own permanent, unforgettable shape into the eternal fabric of the universe. To extend our journey into this timeless landscape, we must now confront the ultimate conceptual frontier, where this illusion breaks down completely. We have observed the elasticity of time through the lenses of relativity and neuroscience, and we have witnessed its outright disappearance within the mathematics of quantum gravity. But if time is an emergent property, a secondary mirage generated by a deeper static reality, we are forced to ask a question that pushes theoretical physics to its absolute limits. What happens at the literal edges of the universe? What does reality look like when the emergent fabric of space-time is subjected to conditions so violent, dense, and extreme that the illusion can no longer sustain itself? To find out, we must journey to two cosmic destinations where the clock does not merely tick at a different rate, but where the very concept of a sequential moment suffers a catastrophic, irreversible structural collapse. The first of these destinations is the event horizon of a supermassive black hole. The second is the absolute beginning of our cosmic narrative, the Big Bang singularity. In the ordinary world described by classical physics, we treat space and time as an open field where an object can move freely in any direction. If you're walking down a street, you can choose to take a step forward, turn around and walk backward, or stop completely and remain stationary. Your freedom of movement in space is entirely up to you, even if your forward march through time remains relentless. But general relativity demonstrates that gravity is not a traditional force pulling on objects. It is the literal bending of the four-dimensional geometry of spacetime. The mass of a heavy object, like a planet or a star, creates a depression in this fabric, forcing other objects to alter their trajectories. When a massive star runs out of nuclear fuel and collapses under the unyielding weight of its own gravity, this depression transforms into a bottomless cosmic well. As you approach the boundary of a black hole, the event horizon, the warping of space-time becomes so pronounced that the roles of space and time undergo a terrifying mathematical inversion. Imagine an astronaut named Sarah drifting toward the event horizon of a black hole, while a colleague named Michael watches her descent from a safe distance aboard a stationary starship far away. Because gravity warps time, Michael will see Sarah's personal clock begin to slow down dramatically as she approaches the boundary. From Michael's perspective, as Sarah gets closer and closer to the event horizon, the light waves reflecting off her spacesuit take longer and longer to escape the gravitational well. To Michael, Sarah appears to slow down to a crawl. Her gestures become glacial. The intervals between her heartbeats stretch into hours, and the light shifting away from her shifts into longer, redder wavelengths. As she reaches the absolute edge of the horizon, Michael sees her freeze completely, suspended like a permanent photograph on the threshold of the abyss, fading slowly into a dim, ghostly silhouette. From the perspective of the outside universe, Sarah never actually crosses the event horizon. She remains trapped at the literal end of time forever. But Sarah's internal experience is completely different. Because her personal frame of reference moves with her, she doesn't feel her clock slowing down at all. Her heart beats at its normal pace, her thoughts flow smoothly, and she passes through the event horizon without feeling a sudden hitch or bump at the boundary line. However, the moment she crosses that threshold, the geometry of the universe undergoes a radical, irreversible transformation. Inside the event horizon, the gravitational warping is so intense that the radial direction leading toward the central singularity becomes completely decoupled from standard space. The mathematical equations of general relativity demonstrate that inside a black hole, the coordinate representing space and the coordinate representing time literally swap their algebraic signs. What was once a spatial direction becomes a temporal direction. Think about what this means for Sarah's reality. Outside the black hole, the singularity was a place located somewhere in space. Inside the event horizon, the singularity is no longer a place in space. It is an inescapable moment in time. Just as you cannot turn around and walk backward into yesterday, Sarah cannot turn her thrusters around and fly away from the center of the black hole. Moving toward the singularity is no longer a choice of navigation. It is the literal future. Attempting to escape the center of a black hole is exactly as impossible as attempting to escape next Tuesday. Space has become time, and the path forward is a one-way street leading toward a cosmic deadline where the fabric of space-time itself is torn to shreds. At the exact center of this trap sits the singularity, a point where the equations of general relativity state that the density of matter becomes infinite and the volume of space shrinks to absolute zero. At this mathematical boundary, the curvature of spacetime becomes infinite, which means that the very coordinates we use to define where and when completely break down. The block universe hits a literal wall. The fabric of spacetime is not just stretched, it is punctured. Relativity simply stops working, confessing its own inability to describe the true nature of reality without a deeper quantum framework. To understand what truly happens at this point of collapse, modern physicists look away from black holes and turn their attention to the grandest singularity of them all, the Big Bang. We are accustomed to thinking of the Big Bang as an explosion that occurred inside an empty, pre-existing room, a sudden flash of light and matter that expanded outward into a vast, dark void. But this is a fundamental misunderstanding of cosmology. The Big Bang did not happen in space, and it did not happen in time. The Big Bang was the simultaneous creation of space and time themselves. If you take the observed expansion of the universe today and run the cosmic film strip backward in time, you will see all the galaxies, stars, and dark matter drawing closer and closer together. As you travel back past 13.8 billion years, the entire observable universe is compressed into a region smaller than an atom, then smaller than a subatomic particle, approaching a state of infinite heat and infinite density. If you try to ask what happened before the Big Bang, you are committing a logical error that is identical to asking what is located 1 kilometer north of the North Pole. The question sounds grammatically correct, but it betrays a deep misunderstanding of the underlying geometry. At the North Pole, every single direction you can possibly look or walk is south. There is no north of the North Pole because the coordinate system itself originates at that point. Similarly, there is no before the Big Bang because the temporal coordinate system of our universe originates at that initial boundary. However, when physicists attempt to use the tools of quantum mechanics to look directly at this cosmic origin point, the neat boundary of the Big Bang singularity begins to dissolve into something far stranger. In the 1980s, Stephen Hawking and James Hartle proposed a radical model known as the no boundary proposal. They suggested that if you travel back toward the absolute beginning of the universe, the distinction between space and time completely vanishes. In the high energy, high density crucible of the early universe, the real time coordinate that we experience today transforms mathematically into an imaginary time coordinate. In physics, imaginary time is not a mystical concept. It is a mathematical tool where time is treated as if it were a fourth dimension of space. According to the Hartle-Hawking no-boundary proposal, as you approach the absolute dawn of creation, the temporal dimension rounds off smoothly, much like the curved bottom of a smooth teacup. If you walk toward the bottom of a teacup, you never hit a sharp edge, a sudden puncture, or a mathematical singularity. The surface simply curves around smoothly until it becomes flat. In this model, the universe has no sharp beginning point, no initial moment where a clock started ticking, and no creator required to set the gears in motion. The universe is completely self-contained, a timeless four-dimensional space that smoothly transitions into a universe with an emergent arrow of time as it expands. The beginning of time is revealed to be nothing more than a geometric feature of a grander, timeless landscape. This brings us to a profound realization that connects the cosmic scale of the Big Bang directly to the internal architecture of our own minds. If the universe at its deepest levels is fundamentally a timeless, interconnected network of quantum information, why do we experience such a fierce, unyielding sense of the present moment? Why are our brains so utterly obsessed with tracking duration? The answer lies in a concept that bridges thermodynamics, information theory, and cognitive biology: the cost of keeping time. We have noted that the brain possesses a decentralized network of internal clocks, from the circadian rhythm of the suprachiasmatic nucleus to the rapid microsecond calculations of the cerebellum. But what we rarely consider is that running these internal metronomes requires an enormous continuous expenditure of energy. To maintain a steady internal rhythm, a neuron must constantly pump sodium and potassium ions across its cell membrane, building up an electrical gradient that can be discharged to create a signal. This process relies on a molecule called adenosine triphosphate, or ATP, the fundamental energy currency of biological life. Every single tick of your internal clock, every frame of the conscious now that your brain assembles, requires the burning of millions of ATP molecules. Your brain, which represents only about 2% of your total body weight, consumes roughly 20% of your body's total energy supply, and a massive portion of that energy budget is dedicated purely to tracking and processing the passage of time. In recent years, a field of research known as the thermodynamics of timekeeping has demonstrated that this energy cost is not a unique flaw of biological systems. It is a universal law of nature. Whether you are looking at a biological neuron, a mechanical pendulum clock, a digital quartz wristwatch, or a hyper-precise cesium atomic clock, the accuracy of a timekeeping device is fundamentally limited by the amount of energy it consumes and the amount of entropy it exports into the environment. A team of physicists, led by Natalia Ares at the University of Oxford, conducted an extraordinary experiment using a tiny, custom built mechanical clock, a thin membrane suspended over an electronic circuit. They systematically measured the relationship between the clock's accuracy and the amount of heat energy pumped into the system. The data confirmed a precise mathematical correlation. The more accurate you want a clock to be, the more energy it must burn, and the more entropy it must dump into the surrounding world. Think about the profound irony of this physical law. The arrow of time is defined by the steady, inevitable increase of entropy across the cosmos. A clock is an instrument built specifically to measure this forward march. Yet, in the very act of measuring time, the clock must actively accelerate the destruction of order, pumping fresh entropy into the universe just to register the passing of a second. The tools we use to track the flow of reality are themselves contributing to its eventual thermal death. You cannot know the time without paying a tax in cosmic disorder. For a biological organism, this energetic tax means that time tracking is a high stakes survival game. If an animal's brain spends too much energy tracking duration with hyper precise resolution, it will starve. If it spends too little energy, its internal predictions will fail, and it will be caught by a predator or miss an opportunity to find food. Human consciousness evolved to process time at a specific medium resolution scale because that scale represents the sweet spot of evolutionary efficiency. We do not see the quantum superpositions or the static block architecture of spacetime because processing that level of ultimate reality would require an biological brain the size of a planet, burning more energy than a star. We see a simple sequential narrative because it is the most affordable way to stay alive. This evolutionary compression becomes deeply evident when we look at how our brains handle the relationship between time and space within our internal psychological maps. Our minds are so fundamentally ill equipped to handle the concept of pure, abstract duration that we are forced to borrow the language and architecture of space just to think about time at all. Think about how you talk about your life. You look forward to a promotion next month. You look back on your college years. You leave your regrets behind you. If a project takes a significant duration, you describe it as a long meeting, using a spatial adjective to define a temporal experience. In our minds, the timeline of our lives is conceptualized as a physical path stretching through space. This linguistic crosstalk is mirrored by a striking anatomical reality inside your brain. The hippocampus, the curved structure tucked deep within the temporal lobes, is famous for its critical role in forming long-term memories, but it is also the literal GPS system of your mind. The hippocampus contains specialized cells known as place cells and grid cells. These neurons fire in precise geometric patterns, creating a dynamic, real-time map of your physical environment as you walk through a room or navigate a city. In the late 2010s, neuroscientists discovered that these exact same place and grid cells do not just map coordinates in space, they also map coordinates in time. When an animal remains stationary but waits for a specific duration, these hippocampal neurons fire in a sequential rhythmic pattern acting as time cells that track the passing intervals. The brain uses the exact same neural canvas to paint its map of the physical world as it does to paint its map of history. Memory, space, and time are processed by the exact same biological hardware. We are walking through our memories using the same internal machinery we use to walk down a street. This structural overlap explains a fascinating psychological phenomenon known as the spatial agency effect. Studies have shown that if you ask a person to think about an event that will happen in the future, their body will unconsciously lean slightly forward, tilting its weight toward the toes. If you ask them to deeply recall a poignant memory from their childhood, their body will unconsciously shift its weight backward onto the heels. The mind treats the temporal journey as a literal physical movement through space, leaning its physical frame toward the coordinates it is trying to explore. What happens when we take this spatial understanding of time and use it to reevaluate our deep cultural anxieties surrounding productivity, accomplishment, and the relentless speed of modern life? We live in an era dominated by hyper efficiency. We slice our days into 15-minute blocks, sync our calendars across multiple digital devices, and measure our worth by how much output we can generate within a given unit of duration. We treat time as a scarce, finite resource that is constantly running out, a currency that must be spent, saved, or wasted. This collective anxiety is born from the classical mechanical worldview that has dominated human civilization since the Industrial Revolution. When Isaac Newton declared that time was an absolute, independent conveyor belt moving uniformly through the cosmos, he provided the perfect ideological framework for the modern factory clock. We began to treat time as a cold, objective tyrant that exists outside of us, an unyielding matrix to which human life must be violently subjugated. But the combined insights of modern physics and neuroscience offer a radical liberation from this mechanical prison. If time is an emergent projection born from quantum relationships, and if the speed of its passage is completely dictated by the resolution at which your brain samples its environment, then the idea of an objective, universal pace of life is a complete fiction. There is no single correct speed at which a human life should unfold. When you feel overwhelmed by the frantic, accelerating pace of the modern world, you are not failing to keep up with an absolute cosmic clock. You are experiencing a mismatch between the frantic sampling rate of a technological society and the natural biological rhythms of your evolutionary hardware. The digital devices in your palm are designed to operate at the speed of electronic currents, firing information at you in microsecond bursts. When your brain attempts to process this relentless torrent of data, it is forced to ramp up its internal predictive machinery, sampling the environment at a frantic, hyperdense resolution. As we observed with the physics of timekeeping, this hyperfixation causes your internal psychological clock to elongate the experience of stress, making a single day of frantic multitasking feel like an exhausting, prolonged ordeal, while simultaneously leaving your memory books completely blank of any meaningful landmarks. The ultimate antidote to this modern acceleration is not to find a more efficient calendar app. It is to actively step off the mechanical conveyor belt and reclaim your role as the conscious author of your internal duration. You can slow the clock down simply by changing the nature of your interaction with the world. This is the deep structural secret behind the practice of mindfulness and deep meditation that has been observed for thousands of years. When a practiced meditator sits in silence, focusing their absolute attention on the simple, raw sensation of a single breath, they are doing something radical to their internal neural software. They are systematically turning off the brain's predictive default mode network. They stop comparing the present frame against the memories of the past. They stop projecting hypothetical simulations into the future. By dropping the sampling rate of prediction and focusing entirely on the unedited present, the internal stopwatch slows its rhythm. The boundary lines of the ego dissolve, the frantic acceleration of the years drops away, and the mind touches a localized state of absolute stillness that mirrors the timeless tranquility of the quantum underworld. As we stand back and gaze at the complete arc of this exploration, the grand architecture of reality reveals itself to be a stunning, paradoxical circle. We started our journey in the ordinary world of common sense, feeling entirely certain that we were solid passengers, riding a smooth, unyielding river of time from the past into the future. Yet, when we followed that river to its source, the water vanished. Physics dismantled the universal clock, showing that every observer carries their own personal frame of reference and fused space and time into a static, four-dimensional block where all events exist simultaneously. Quantum mechanics pushed deeper, demonstrating that the past is a fluid wave of probability waiting for a measurement in the present to call it into being, and suggested that space-time itself is a secondary hologram generated by a deeper network of quantum information. Meanwhile, neuroscience turned its tools inward, revealing that our internal sense of a continuous present is an edited, delayed broadcast manufactured by a decentralized network of biological timekeepers, fueled by energy, and optimized not for historical accuracy, but for evolutionary survival. We are left with a worldview that is infinitely more majestic, mysterious, and beautifully strange than the simple mechanical clockwork of our ancestors. The universe is not a dead machine ticking away toward an inevitable expiration date. It is a living, interconnected matrix of information whose structure is deeply intertwined with the act of observation itself. The next time you look down at your wrist or glance at the digital clock on your wall, remember the hidden room that sits behind those numbers. Remember that the second hand is not measuring a relentless force that is erasing your life. It is counting the internal dance of atoms, tracking a human convention that we have layered over the cosmos to find our way through the dark. Your past is not gone. It is a permanent coordinate in the beautiful geometry of space-time. Your future is not a terrifying blank void. It is a landscape that is already woven into the structure of reality, waiting for your choices to trace its definitive shape. And your present moment, this very breath, this very thought, this very flash of awareness, is a brilliant holographic masterpiece created by the collaborative genius of the cosmos and your own magnificent brain. We are the timeless universe, discovering how to experience itself one beautiful, fleeting second at a time.